1, 2, 3. 1, 2, 3. Okay, hey guys. So we're going to be solving a version of the diffusion equation today. And we're going to be solving it for the equation u derivative of t is equal to u second derivative of x minus 1 on the boundary x from 0 to 5 with the boundary conditions listed here and the initial condition listed here. So what we're going to want to do first is that we know that the final answer, u of x and t, is going to be a combination of two parts. It's going to be a steady state solution, and we're going to have a Dirichlet solution here. So first we can get started by solving for the steady state solution. So to do that, basically we know that u of s equal to -1 on second derivative equal to +1 on the second derivative right here. So what we can do from that is we can just integrate twice. So we can solve u of s equals x squared over 2, just simple integration, plus a constant times x plus another constant b. Great. So up here. So from here we can just apply the boundary conditions and solve for a and b. So we have u x 0 t equals 0. You can solve for the derivative in your head here, and that will lead us to a is equal to 0. Now we also have u5t is equal to 0. So what that's going to lead to is that b is equal to -5 squared over 2, just by rearranging this equation here, equals -25 over 2. Great. So now we have the steady state solution, u s equals x squared over 2 minus 25 over 2. Great. And that was the inhomogeneous steady state solution part. So now we know that we have the Dirichlet solution part, and that's going to be homogeneous. So we can use separation of variables here, and we can use the ansatz ud equals big X of x, t of t, and basically just plug that into the equation. So we have x of x, t prime of t is equal to x double prime of x, t of t, and so from here we can just solve for this by separation, just separating each side out and get their own differential equations. So we have t prime over t equals x prime double prime over x. And we know that the only way that these two equations could possibly be equal is if we set them equal to a constant. And that's what we'll do. We'll put -k squared for the sake of simplicity and for ease of solving in our solutions. So now we have a couple ordinary differential equations, one first order, one second order. And these will be pretty easy to solve. We just know how to solve t prime equals -k squared t. Going back to the separation of variables part, don't need the -1 because we solved that in our steady state solution. Hope that makes things a little clearer. So it's a lot simpler now to just see how everything connects. So back here. So we have t prime equals negative k squared t, so pretty simple. As we've learned in previous units in this course, we have t equals a e to the negative k squared t. And we have x double prime equals negative k squared x. And basically what we've learned with second order differential equations is that we're going to get e to the negative something using our characteristic equations there. And in the end, we're going to get a solution in the form of x equals b sine kx plus c cosine kx using Euler's identity. So now we can just use our boundary conditions again, and we'll have x0 t equals, we're just taking the derivative kind of quickly here, cosine c sine 0 equals 0, and since this part equals, it just automatically cancels out to 0, we know that b must equal 0. Great. So let's move up on the page. And now we use our other boundary condition. We have u of 5 and t equals c cosine 5k, and that equals 0. And so what we want here is we want 5k, this 5k in here to be whatever cosine has to be to equal 0. So we know that cosine equals 0 when cosine is equal to pi over 2, 3 pi over 2, and so on. So we set 5k is equal to n pi plus pi over 2. N, of course, is an integer. We usually use positive integers for this, for series, of course. So just to remember that. So then we solve for k. So we have k is equal to n pi plus pi over 2 over 5. Great. So now we can put our two solutions together. We're almost done. We just need to solve for c now. So we have u equals us plus ud equals x squared over 2 minus 25 over 2 plus. Then we have our series because we have an n here, so we're going to want all the solutions including this n. So n equals 1 to infinity cn cosine kx e to the negative k squared t. Great. And obviously k is just our solution here. And now we can plug in our initial condition from the beginning of the problem to solve for c. So we have our initial condition was u of x and t equals 0 equals x squared times 25 minus x squared. So at that point, we're going to have x squared times 25 minus x squared is going to be equal to this equation above without this part. This part is going to be 1. So we can just rearrange, and I'll write it out fully for you guys. So x squared times 25 minus x squared minus x squared over 2 plus 25 over 2 is equal to sum to trinity of C sub n cosine kx. Great, and then the final part we want to know is what's the value of C. So here we can just use the inner product as we've learned in the last unit in this class to find C. We won't do it out, but here we'll say C sub n is equal to inner product of the left side of the equation times cosine over cosine of x Great. And there you have it. That's the final solution to U, solving the diffusion equation, finding the values of the coefficients by using the boundary conditions and the initial conditions. We found U right here, we found C here, and we found K right here. And then you just put them all together, and there you have it.